Our next talk is by Jie Liu from MSS Beijing. So he will talk about symplectic singularities arising from the algebra of symmetric tensors. Please.
Okay. Thanks for the introduction, and also I would like to thank the organizers for the invitation. And it's my great honor to give a talk in this very nice conference, and also in this very nice campus. So today I'm going to talk about some joint work with Baohua Fu from Chinese Academy of Science to talk about to construct some symplectic singularities using the so-called algebras of symmetric tensors. So for my talk, I will always work over the complex numbers. Let me start with the basic definitions of symplectic singularities, which should be well known for experts. So this notion is introduced by Beauvais around 2000. So we start with some normal variety V. Normal variety. So V is called symplectic or has symplectic singularity. If, first of all, you need to find some symplectic form over the smooth locus of this V. You can find some symplectic form over the smooth locus of V. And then you also require that for any resolution of V, resolution, this symplectic form omega extends to a two-form, holomorphic two-form over this resolution Z. But this two-form may be not omega Z. This two-form may be not symplectic, okay? Maybe not symplectic. So if you have some symplectic variety, and you take some resolution such that the extension of this symplectic form on Z to be symplectic, then we will call this Z to be a symplectic resolution of V. So if omega Z is symplectic again, we will call Z a symplectic resolution. Okay, so this is the definition of the symplectic singularities and also the symplectic resolution. So let me just introduce some very basic examples. First of all, we look at a case where V is smooth, or in smooth case. So the first example I want to talk about is the codine bundle of the affine space Tn. So this can be identified to the product Cn times the dual of Cn. Okay. So we can take the coordinates C1 to Cn on this Cn, and also its dual coordinates y1 to yn. Okay. And in this case, you can define your symplectic form to be the standard one, to be the sigma dxi y dyi. Okay. This is the first example I want to talk. In fact, this construction can be generalized to any smooth variety x. So you can take x to be any smooth variety. And I take, you look at the codine bundle of this x. So now you can define a standard symplectic form over this codine space, which is d omega, d eta. Eta is the so-called Milware form. Okay, so locally this one is nothing else but if you look at this x locally, so you get the standard one effect. So locally, this is just equals to the first example. Okay, this is about the smooth case. Now I want to talk about the singular case. So first of all, we look at the two-dimensional case. So we look at the case where V is a two-dimensional normal variety. In this case, the symplectic singularity is very easy, so it's just the so-called dual singularity. So it's just the dual singularities. Okay, and on the other hand, we can also construct the symplectic form, use symplectic singularities, use the so-called quotient. So we take C2n 0, sorry, omega as in this example, as in the smooth example, sorry. Maybe I need to take 3, 4, as in the first example, okay? And then you take an infinite group in the symplectic group, okay? And you take the quotient of this one. And then this symplectic form descends to this quotient. It worked well. Maybe I need to. Hello? It's okay? Okay, so in this case, the symplectic form descends to this quotient, so give you some, in general, give you some singular symplectic varieties. Okay, this is, sorry.
Maybe try to
I need to, okay. So I'll keep, maybe I use this two blackboards only. Okay, sorry. Sorry, I cannot use this blackboard. Sorry. So another example I want to talk about the so-called nilpotent orbit. You just take any same sample, Lie algebra, and you consider the adjoint action of G over this Lie algebra, and take any nilpotent orbit. So you take any element in this G, and which is called nilpotent. If it's the co-adjoint action, so this G to G, which is defined by V, is some nilpotent. This one is some nilpotent linear action. Okay, and then you take the orbit of this V under this co-adjoint action. You take O of V to be the orbit of V in this G. Okay, and over this smooth variety, this one is smooth. You have some symplectic form over this one. So you get some symplectic form. Symplectic form over this orbit, which is called the, have a name for this one, which is called the, maybe I write down. which is called the Coston, Krylov, and Sovia form. Okay. So if you want to get a singularity, you just take the closure of this one. This is in general, this one is not closed in this one. So you just take the closure of this orbit in G. Okay. Right. If you take the closure, in general you get some singularity, but maybe not normal. Okay. So you take its normalization. You take the normalization. And then, in fact, it can be proved that this symplectic form over this closure can be lifted to this normalization. Okay, this I think this is done by Hanshef. So I show that this normalization of this nilpotent, the closure of this nilpotent comb is symplectic. Okay, let me just show you some explicit example in this case, in the SL2 case. So, sorry, I don't know. I don't know any explicit example, but I think in many cases there are some. Maybe Professor Nakawa, do you know any explicit example where the closure is not normal? The closure of this one is not normal. Any explicit example?
There is some exceptional E algebra.
I don't know explicit example.
But is listed.
Yeah, I think we can describe all of them, right? No, I'm not so sure. Maybe the. Okay. Yeah, I think there are some examples. Yeah. But I don't know any explicit example in this case. I just look at this very easy, simple cases, where G is the SL2 case. Okay, you just look at the 2 times 2 matrix, traceless 2 times 2 matrix, x minus x, y, z. Okay, and you can show that this matrix A is nilpotent if and only if the determinant of A is equal to 0. Okay, so this just to give you some equation in C3, x squared plus yz equals to 0 in C3. Okay. So in this case, you look at the matrix 1, 0, 1, 0, 0. Okay, wait to be this one, and you take the closure of this one, and this gives you some comb in C3, quadratic comb. Okay, and you take the orbit of this spatial matrix. In fact, it's just this comb moves the zero matrix. Okay. So if you take the closure of this one, you just get the whole comb, quadratic comb here. So you take the closure of this one, you get the whole comb N here, and which is also normal, so its normalization itself. Okay. So this is some explicit example in this one. So far, any questions? So now I want to introduce some other constructions for this kind of singularities, which is we will use the so-called moment map. So you consider any smooth right x, and you consider some linear algebraic group acting on this variety x. Okay, For any point small x in this variety x, you consider the orbit map from G to G times x. Okay, and then you look at the tangent map of this orbital map at the identity. So give a linear map from the linear algebra of G to the tangent space of this x of this orbit, which of course is the subspace of the tangent space of x of at x here. Okay, now you take the dual of this one. You just take the dual of this. Of this linear map. You take the dual of this map. So get a map, linear map from the coordinate space of x at this small x to the dual of the linear algebra of G. Okay, and then you group this together. You put this together. You get a map from the coordinate of x to the dual of G. Okay, this is called the moment map of this action G on X. This is called the moment map. Now I want to give you some explicit example of this kind of stuff, which is very interesting and important. Which is, the first one is the so-called spring map. So in this case, you take X to be any rational homogeneous space. Rational homogeneous space. Homogeneous space. So G is some simple semi-simple Lie group, algebraic group, and I take P to be some parabolic subgroup. Okay, and in this case, you can show that the coordinate model of X can be written down explicitly. So the coordinate model of X can be written down as a homogeneous vector bundle of this G modulo P dual. Okay, so you have a very natural inclusion of this one to the G times P times G star, and I take the linear projection to the second factor. So it gets a moment map in this special case. And you look at the image of this one. Okay, so this will give you, in fact, the image of this one. So a result of Richardson. Just that this image is in fact some nilpotent, the closure of some nilpotent orbit. So the image of this map back here is just the closure of some nilpotent orbit. Nilpotent orbit. OV. Okay. Sorry. Here. Sorry. I need to take the dual. Sorry, I need to take the dual. I need to use the Kelvin form to get an isomorphism between the dual of G and the G. Okay, and then you look at the image of this one. Okay. Here. Okay. And this map from phi to the tangent mod of G over P to this image is in fact a proper finite, generically finite morphism, proper, and also generically finite morphism. Okay. So now, since this is a proper map, so you can take the standard factorization of this map. I take the standard factorization. I think in type B. Sorry. I think in type A this map I think is always birational, but in type B there are many examples this map is not birational. I think even for exceptional cases there are many cases this one is also not birational. We do have a classification of this kind of stuff. We can compare to their degrees or anything else. So now you just take the stem factorization of the height to this OV. Take the stem factorization. You get a phi height here. So look at this one. This in fact, this is birational, right? Proper. So this in fact is give you some example of symplectic resolution. Example of symplectic resolution. Okay. We go back to the quadratic cone example. Sorry?
This case, all bar and all head are symplectic singularities?
Yeah. Because this is in fact, this one maybe not normal, I mean. This is some direct finite cover of this one. This one is always normal because you take the stem factorization. In fact, this OV height is nothing else but a spike of the ring of regular functions over this cosine bundle. Yeah. So, of course, this one is symplectic because this is a birational map. You can take any symplectic form over this to give cells, which will descend to this OV height. But this one maybe not normal. Yeah, that's a problem. Yeah.
This finite map, isn't it
I'm not so sure. In some special case, I know this is some Galois group, but Galois quotient. But in a general case, I don't know. I don't know if it's Galois or not. So. Which one? This? Of course, this is a cosine bundle of some smooth variety. Yeah. Because you look at the canonical bundle of this one is trivial, because you have some, you have some symplectic form here. Yeah, this is In fact, the symplectic resolution is always quadrant, because the canonical bundle is always trivial at two sides. Yeah. So, any other questions? So let me go back to the quadratic cone case. In this case, you just take X G, the homogeneous space to be the projective line P1. And in fact, we have a map here from the T star of P1 go to the quadratic cone. X squared plus YZ equals to 0 in C3. Okay, you get to the quadratic cone. And look at this one. This is so. In fact, this is just the contraction of the zero section. And this one is in fact the blow up of this quadratic cone. So this is the first example I want to say, to use the so-called moment mapper to construct symplectic singularities, even for symplectic resolutions. And right now I want to talk about another construction of symplectic varieties using this kind of map, which is the so-called hypertoric variety. I think this will also appear in the talk of Professor Namikawa. So the second example I want to talk is this hyperbolic variety. So you take a torus of dimension r, okay, which acts on the affine space Cn. So you take a coordinates here, t1 to tr, and the coordinates here, x1 to xn. Okay, you write down the weight of this action of ti on each coordinate. I will write it as ai1 to ain. Okay, and then you get a matrix A. So yeah, this is the weight of ti on the coordinates x1, and this is the weight of ti x on this coordinate same. Yeah. So you get some matrix A, so which is aij. Yeah. I is from 1 to r. Yeah. So it gets 1 from I from 1 to r, j is from 1 to n. Okay. And I will write down it as something like this. This is the first column, and this is the last column. Okay. So then I can write down explicitly what's the moment map of this action on this codine bundle. So look at T star Cn. Again, you write down it as the product of Cn with its dual, with the coordinates here, x1 to xn, and here it's y1 to yn. Okay. To the Lie algebra of this torus, which can be written down as CR, right? Which is just a CR. Okay. This pipe, in fact, is just the sum of this AI, the vector AI times xi, yi. Okay. You have an R equation here, because this is a vector. You get R equation here. Now you look at the preimage of the zero. You look at the quotient of ya of zero, which is defined to be the preimage of zero under this moment map modulo by the action of t. So this is your moment map phi here. You take the preimage of this one, and I take omega to be a standard symplectic form over this T star Cn, and a result by Bellamy in the last year. We show that if you can prove that this preimage is reducible, then this quotient should be symplectic. So if this one is irreducible, then this ya0 together with the quotient of this symplectic form will be symplectic, be a symplectic variety. So this is induced by the standard symplectic form over this T star Cn.
This is the affine quotient.
Yeah, GIT quotient. Yeah, invariant quotient. So this is some affine space. You just take the ring of invariance of this action. Yeah. So for this kind of variety, this is studied intensively in the literature. For example, we know when this variety has symplectic resolution. This is, in fact, this is a work by Professor Namikawa in the last year. He gave a complete characterization of YA0 admitting a symplectic resolution. Okay, so for this kind of symplectic variety, I think we have lacked by the understanding of their geometries. But in general, the symplectic varieties are quite complicated. So now, today I want to present a new method to construct symplectic singularities. So now I want to talk about our work. We give you a new construction of symplectic singularities. Actually, the idea of this construction is very easy. In fact, if you want to construct a singularity, that's quite easy, right? You take an arbitrary variety. In general, it should be singular. But the problem is that you need to find some symmetrical form over its rigorous locus. In general, this is quite difficult. So the general idea is we start with some variety, smooth, maybe smooth, with symplectic form, and we try to do some birational modification of this smooth guys, and you get something right. It is under this birational modification, and then you try to prove that it has good singularities. I mean, this symplectic form can be extended to any resolution. This is our idea. So what we use is try to generalize the Springer map effect. Idea. We want to generalize the Springer map. Okay. So just recall that how to construct singularities for the codine model of G modular P. We just take phi height, which is just a spike. The ring of regular functions of this codine bundle of G modular P, which is way height. Okay. So you start with some smooth variety with symplectic forms, and you try to do some birational construction. You get a single variety. You prove that this has good singularities as you like. So we want to generalize this construction directly, revelational. So we just consider this map for any x. So you look at x to be any smooth variety. You just look at the ring of regular functions over the codine model of x. Okay, ring of regular functions. This codine model of x. Okay. And you have some other interpretation of this ring. You can also write it down as the so-called symmetric, the algebra of symmetric tensor. So, which is the gradient ring of the global sections of the symmetrical parts of the tangent model of x. So this is the algebra of symmetric tensor, of symmetric tensors. Okay, this is the object appeared in my talk, in the title of my talk. And you can also write down as the section ring, the ring of sections, of P of Tx, OP of Tx 1, which is just the ring of sections of the approach of the tangent model of x, the tautological bound of the tangent model of x. So it's the ring of sections. So we have 3 different point of view of this ring. So for me, I prefer this one in general. So that's why I call it, why I call, we want to construct symplectic singularities using the algebra of symmetric tensors. So any questions? Now, as the spring map, we just consider the natural map from the coordinate bundle X to this spike of this ring. We look at this map from the spike of this, the ring of regular functions on this one. So this is also spike of the algebra of symmetrical tensors. So I will denote this by z of x. So be careful. In general, we don't know if this ring is finitely generated. So this is just some scheme, normal affine scheme. Of course, this map is dominant. Now, in general, it's not surjective, but not surjective in general. Okay. And now we want to see in which cases this variety is in fact a symplectic variety. So first of all, I want to find some symplectic form over this one. So in this case, I want to use the symplectic form on T star x to give a symplectic form on this one. So at least I need to this map to be birational. So the first question I want to ask you is, sorry? Which one? Any x. Yeah, right now just any x. Yeah, it may be very large, but the dimension is always bounded by 2 times the dimension of x. Yeah. I mean, when. So finally, I will only consider the projective case. But right now, it works for any smooth varieties. One is this map phi birational. Okay. And then you want to ask when this one is finitely generated. In fact, this is asked by Beauville. You want to ask if this is always true. This algebra is finitely generated. Okay. Is this one finitely generated over the complex numbers? I don't know answers, but for all the examples we learn, this ring is always, this algebra is always finitely generated. Okay? And then I want to ask 1 plus 2, okay? We want to ask this symplectic. So when this z of x is symplectic. So now I can state our main theories. Sorry?
Doesn't 3 follow automatically from 1 and 2? I mean, you have a form on an open subset and it extends on this.
No, it's not automatic. I mean, first of all, at least I want to construct some symplectic form over some large open subsets, but it's not clear if it can be extended to the regular locus of this variety. No, that's not clear in general. Yeah.
So you mean it is defined on some open subset, but not necessarily on.
Yeah, a priori, yes. You still need some work to do this kind of things. Yeah. But I will say that in general, for projective one, this is almost automatic phenomenon. The problem is that this map is not surjective, so that's a main problem. So it's, the boundary may be very big and even a divisor or something like that. Yeah. So I want to state our first result. Okay. So this is the majority with Baohua. First of all, we have a very at least for x to be right now. I will focus on the case where x is a projective manifold. Okay, and then we have a complete answer for the first question. We can answer when this one is birational. Okay, and then this map is birational if and only if the tiny amount of x is so-called big. So this just means that the tautological boundary of this approach of Tx is a big line boundary. Okay. And for the second question, I don't know the answer in the general, but if you compare the second with the third, we ask when this one is a variety and it's symplectic, we have a complete answer in this case. So this, so if x birational plus this symplectic, if and only if the approach of Tx is of follow type. So let me recall the definition of varieties of. Yeah. This is true for any vector boundary effects. Yeah. You're right. Just a translation of the general result. Yeah, this is true in fact for any vector boundary. Yeah. So let me recall the definition for varieties of file type. So you consider some x, y of projective manifold or any normal variety. So y is called a file type. Just means you can find some Q divisors. Q divisor, delta, effective Q divisor, such that this pair y delta is QT, and also the minus ky plus delta. Example. Yeah. One typical example of this one is just you consider the any weak follow. Okay, implies follow type. Weak follow just means minus ky is big enough. Okay, so this is some generalization of the follow manifolds. So once we can prove this kind of result, we want. I think for any toric varieties. You just take any big minus kx, and I take some smooth guy here, d here, and I take m minus d. Yeah. Maybe not. Sorry, I want to write down it. Sorry, ky can be written down as some, ample plus some very small delta. Very small. Because this one is big enough. For any big enough divisor, you can find some very small effective Q divisor, such as the difference of this one example. So you just take this delta. Because this is smooth, so this one is only QT. QT is an open condition, you take a small boundary, it's still QT. Yeah. Yeah. I mean, for symplectic variety, I always suppose it's a variety, so it's finite generated. Yeah. So this algebra shows finite generated. This is contained in the definition of symplectic varieties. Yeah. So once we have such kind of result, you want to ask, do we have such kind of sample? For example, it's maybe empty, right? Yeah. In fact, we do have that kind of example. Yeah. I will give you this kind of example. Yeah. Sorry. Yeah. Definitely. Thank you. Yeah. The first example we can work out is weak follow kind of things. So I take x to be G mod P. In this case, in fact, the product of Tx is a weak follow. Yeah. So this is the first example we can find. Okay, because in this case you have OP, you have minus K P of Tx, because it's isomorphic to the P Tx of n. N is the dimension of x. Okay. For a rational homogeneous space, this one is always big enough. So this is a weak follow method. And in fact, I think besides this example, we don't have too much example known in the literature before. I think the only one I can find is, in fact, an example which is found by Horan and Peterman in the last year. They show that for X2 to be the quantic dipiezo threefold, quantic dipiezo threefold, this is okay. Here, the quantic dipiezo threefold just the intersections of the Grassmannian 2, 5. I don't know, in fact. I don't know, good question, but I don't know, in fact. Yeah. In fact, here just means V5, which is isomorphic to the intersection of Grassmannian 5 in P9. Yeah, because for that quantiple dipiezo method, we know that its tangent boundary is big, but we don't know if it's a file type or not. Even I don't know if it's this ring is a finite rate or not. Yeah. So now I want to state our second result. We find some other example in this kind of in this category. First of all, we prove that in fact for all toric variety, okay, P of Tx of file type, if x is one of the following. First of all, this is for any smooth projective toric variety. So this P of Tx is a file type. Yeah, in fact, it's known that all the toric varieties are for file type. But for the project of the tangent bundle, I think this is non-trivial. And another example we can find is that the so-called holospheric projective holospheric variety with a small boundary, Okay, I don't want to explain what the holospheric variety is, but we know that this one is a quasi-homogeneous, some spatial quasi-homogeneous variety. Spatial quasi-homogeneous. Homogeneous variety. Okay, and the small boundary means that the open orbit is quite large. That means the complement of this open orbit has a codimension at least 2 in this X. Okay. For some, I think for some subsample group. I think this is in the definition of holospheric variety. You consider the action of some subsample linear. But here I don't need to consider the subsample part. Yeah, I cannot consider the. I think we need to use it to to control the geometry of the boundary. In fact, we need to control the moment map under this group action. If it's shape sample, we can easily control the moment map of this G action. Otherwise, for a general map, this moment map is quite complicated, and we cannot control the geometry of this action in our divisor. Yeah, and this condition is this condition, small boundary condition, is satisfied. For example, if the peak number is 1. Okay, so if it's it's a smooth projective for the circularity with peak number 1, its boundary is always smooth. I think, let me check. For the circularity, I mean, we do have a classification. I think there are some linear section of some spatial GMOP. I forget. We have a classification of peak number 1 case. Yeah. And so right now I want to move to the last result. We use this kind of things. We can construct some examples of symplectic varieties, and we want to ask all these examples, do they have any relations with the previous construction? In fact, in the torical case, we can prove that this is exactly the hypertorical variety we have constructed before. So our last survey. We show that if X is the smooth projective torical variety, and I take this Zx, in fact, it is isomorphic to some hypertorical variety, YA0. And here A is a matrix defined by the natural exact sequence from the dual lattice to the Z of sigma 1 to the P group of X. And here is your matrix X. A, okay? Yeah. I still have several minutes. Now I want to talk about the idea of the proof. In fact, it's quite easy. So I want to talk about the idea of the proof. Now, for example, for theory A, okay? So by the definition, we get a dominant map from the codine model of X to Z of X, okay? And you take the approach of this codine model, you get P of X. Here I use a different notation comparing with the talk of Jie Liu. I take the projectivization in the sense of coauthentic. Yeah. So here you take this one. This is in fact is the spec of Sx, which is a gradient ring. So you can take the approach of this one. So you get a approach of this X. So which is just a approach of this gradient ring Sx. Okay. And this is nothing else but the Alpha here. And in fact, you can also write down this one, use the other identification of this ring. You can write down that the approach of the section ring of P of X, OP of X 1, okay? And we can replace this by some power of this line bundle. There's no problem. It's in fact the anti-canonical ring of this project minus K P X. Okay. So in fact this is the anti-canonical model. Anti-canonical model of this project of checks. Okay. Then I want to try to translate the information at this side to the information at the right-hand side. In fact, we can prove that we have the following equivalence. So look at here. This has symplectic singularities. Is symplectic. And this map phi is birational. Use some criterion proved by Professor Namikawa. We can show that this is equivalent to prove the following things. First of all, we want to prove this algebra is finite generated. And then we want to prove that you can find some symplectic form over this regular locus of this variety, normal variety. And then you want to prove that this Zx has KLT singularity. And finally, we want to prove that this Tx is big. Okay. And finally, we can show that these 4 conditions can be translated to the following 3 conditions. So which is so the finite generation of this ring can be translated to the finite generation of the anti-canonical ring of P of Tx. And the singularity about Zx can be translated to the singularity of this P of Tx. P of Zx has KLT singularity. And finally, this can be translated to the minus P of Tx is big. Okay? And you can say that this one is automatic under this 3 condition. That means this symplectic form, because it's birational, you get some symplectic form over some open subset of this Zx. But finally, we found that it can be automatically extended to the regular locus of this one. And finally, use some result in birational geometry proved by Gassini, Gongel. This is just to say that P of Tx is of follow type. Okay. Now, for the last minute, maybe maybe I just stop here. So I will leave the proof of the last 2 theories. Yeah. So thank you.
Thank you very much. So are there any questions? So can you say something about the base of phi x in the case where it is not birational? So the affinization.
In fact, we don't have too much examples in this case. In fact, if it's not birational, of course, this one may be trivial. I mean, this one may be the constant. Yes. So it should be a point. Another example we know is that in all the other examples, I think the base should be some affine space. It's very similar to the Hitchin map, in fact. Yeah, we don't know too much examples where we can work out this algebra. We can write that explicitly. Yeah. This is the only examples I know.
So what about the dimension of the base? So in the case, non-trivial case, say x is not the product.
I mean, as we have discussed before, the case I know that right now, for all the examples we know, the dimension is either is big, is maximum, I mean, 2 times the dimension of x, either it's 0, I mean, this algebra is trivial, either it's half dimension, I mean, it's the dimension of x. We don't know too many other examples, so yeah, good question. But I don't know too much. Of course, you can take some product, or you can take some product.
Non-trivial.
Yeah. non-trivial. Of course, you can take some product.
Are there more questions? Oh, yes.
So, in term E, you also have the spherical examples.
Yes.
Did you have an equivalent of theorem C for it? Do you know the new, locally new?
There are some of, first of all the homogeneous ones are homogeneous or holospheric. So, in this trivial example, yes, it can be identified to the sprinkle map. In the non-trivial example, we don't know how to describe it. It's quite complicated. We can write down, for example, the moment map for the automorphism group of this one, but we cannot prove that the image is exactly this. I mean, yeah, this, I don't know. I mean, yeah, I don't know.
More questions? If not, then next is Jie Liu again. Thank you very much.
Thank you.